Hi all, I'm Yasodhara, and in this presentation, I analyze node importance in two different network systems using several centrality measures. So the goal is to analyze how different centrality measures identify important nodes in networks. We evaluate several centrality metrics and compare how they behave across two different types of networks. This helps us understand how network structure affects which nodes are considered important. So for this study, I used two real-world network datasets obtained from the Stanford Large Network Dataset Collection, also known as SNAP. So the first dataset is the email communication network. So in this network, nodes represent email users within a research institution, and edges represent email communications between them. The dataset contains 1,000 nodes and over 25,000 connections, forming a dense social communication network. And the second dataset is the California Road Network. Here, nodes represent road intersections and edges represent road connections between them. This dataset is much larger and represent a spatial transportation network. And using these two different network types, it allows us to observe how centrality measures behave in both social communication networks and physical infrastructure networks. And the visualization on the right here highlight the structural differences between the networks. And I want to add another thing. So here, the road network has like millions of nodes. So I sampled 8,000 nodes from the road network and then extracted the largest connected component, which has like 2,000 nodes to perform the centrality analysis. And yeah, here. So, sorry. So, centrality measures help identify important or influential nodes within a network. And different centrality measures capture different notions of importance. For example, some nodes may be important because they have many connections, while others may be important because they act as bridges between different parts of the network. So in this study, I evaluate five commonly used centrality measures: degree centrality, betweenness, closeness, eigenvector, and page rank. So these measures capture different aspects of node importance, such as connectivity, information flow, and structural influence. And this allows us to analyze how node importance differs between the email communication network and the road transportation network. And in the email communication, degree is like users with many communication contacts. Betweenness is like communication brokers connecting departments, and the closeness shows like users who can quickly reach many others in the network. And eigenvector can show users connected to other influential users, and the page rank normally shows the globally influential users in the communication structure. And when it comes to the road network, degree refers to intersections connected to multiple roads, and the betweenness can implement key intersections that carry large traffic flow. And the closeness can show intersections with a short travel distance to many locations. And the eigenvector says like the intersections connected to important road hubs, and the page rank again, like the intersections frequently encountered in a route traversal. And so the analysis was implemented using Python and several supporting libraries. Network X was used for constructing the networks and computing the centrality measures, and Pandas was used for handling and organizing the computed data. And for the visualization, I used Matplotlib and Seaborn to generate histograms, scatter plots, and correlation heat maps that help analyze and compare the centrality measures across the two data sets. So to analyze the importance of nodes in the network, I computed 5 centrality measures, as I mentioned earlier. Degree centrality measures how many direct connections a node has, and it indicates the local influence. Closeness centrality measures how close a node is to all other nodes in the network, reflecting how quickly it can reach others. And betweenness centrality captures how often a node lies on shortest paths between other nodes, identifying bridge or like the broken nodes that control information flow. And the eigenvector centrality measure influence like the it is based on the connections to other important nodes, and the page rank estimates the probability of reaching a node through random walks, capturing global important in the network. And when page ranking, normally they are like the standard page rank and the personalized page rank, and all in the personalized page rank, um, they like do the random walk and they teleport again, so covering and getting the global influence. Yep. So these measures help identify influential nodes and structural roles in complex networks. And these measures capture different aspects of importance in a network. So degree measures local connectivity, and the closeness measures accessibility, and betweenness identifies the bridges, while eigenvector and PageRank capture global influence through connections to the important nodes. And this slide shows the distribution of the 5 centrality measures in the email network. So most of the distributions are heavily right skewed, meaning that the majority of nodes have very low centrality values. However, a small number of nodes have significantly higher values, and it forms the long tail of the distribution. Here, there's a long tail here, if you can see it. And that indicates the presence of highly influential nodes or hubs in the network. These nodes either have many connections, lie on many shortest communication paths, or are like connected to other important nodes. Such patterns are typical in social and communication networks, where a few individuals play a central role in information flow. So why is closeness more like normally distributed in this case? So closeness depends on average distance to all nodes, so it tends to very less extremely than measures like degree or betweenness, which can produce very large differences for hub nodes. And this slide shows the centrality distribution for the road network. Unlike the email network, the distributions here are much narrower and more concentrated. So most intersections have similar centrality values, and there are very few extreme outliers. This happens because road networks are constrained by physical infrastructure. So an intersection can only connect to a limited number of roads, typically 3 or 4. So as a result, the network does not develop highly dominant hubs like we see in social or communication networks. And maybe like we can say degree is so limited in the road network. So because road intersections are constrained by physical space and road layout, and most nodes connect to only 2 to 4 roads, so which limits the variability of degree centrality. And now this slide shows the relationships between different centrality measures in the email network. In the first plot, degree centrality and page rank show a strong positive relationship. This means like nodes with many connections also tend to have high global importance. The second plot shows degree versus betweenness, where nodes with higher degree often lie on more shortest paths, indicating they act as communication bridges. And the third plot compares closeness and betweenness, showing that nodes closer to the rest of the network also tend to play important roles in information flow. Overall, these relationships suggest that highly connected nodes in the email network often occupy structurally important positions. And this slide shows the relationships between centrality measures in the road network. Compared to the email network, the patterns here are much more constrained and structured. So degree centrality shows only a few discrete values because intersections typically connect to a limited number of roads. As a result, relationships between measures such as degree, page rank, and betweenness are less variable. And the scatter plots also show that while some intersections have higher betweenness, um, indicating key traffic routes, most nodes remain relatively similar in importance. And this slide shows the Spearman rank correlation between the different centrality measures for both networks. In the email network, we observe very strong correlations between almost all centrality measures, and it is often above 0.8 or 0.9. This indicates that influential nodes tend to score highly across multiple measures. In contrast, the road network shows much weaker correlations, and you can see many values are closer to 0.2 or 0.3, meaning the different centrality measures capture different structural roles in the network. And this difference arises because road networks are spatially constrained, while the social networks allow the emergence of highly connected hubs. So this shows that network structure strongly influences how centrality measures behave. And to summarize the results, the email network exhibits highly skewed centrality distribution, where a small number of nodes acts as highly influential hubs, while most nodes remain peripheral. In contrast, the road network is structurally constrained, meaning that intersections can only connect to a limited number of roads. And as a result, centrality values are more uniform, and between centrality highlights the critical intersections that control traffic flow. So overall, this analysis shows that different centrality measures capture different notions of importance depending on the structure of the network. One limitation of this analysis is that we used only one sample for each network type, so the results may not fully generalize to all email or road networks. And in addition, the analysis treats the network as a static structure, and that means we did not consider temporal dynamics or changes in connectivity over time. So for future work, we could analyze large data sets and explore additional centrality measures and study the dynamic network behavior to better understand how importance evolves in real world networks. Yeah, that's all. Thank you.